I guess you can probably see the slides there.
Mm-hmm.
Great. Okay.
All right, so good afternoon, everyone. Today we have the pleasure of listening to Christian Sampson. Dr. Sampson is a postdoctoral fellow at the University of North Carolina, Chapel Hill, working under the direction of Professor Chris Jones. He received his PhD in 2017 from the University of Utah under the direction of Ken Golden. The title of his talk is Ensemble Kalman Filter for Non-Conservative Moving Mesh Solvers with a Joint Physics and Mesh Location Update. So, Dr. Sampson, the floor is yours.
Cool. Thanks, Emmanuel. And thanks to the student chapter for inviting me. It's always fun to be able to give a talk. So I appreciate the opportunity. So yeah, today I'll talk about doing some data assimilation for models that have adaptive meshes. In particular, I'll talk about ensemble and data assimilation, but just some background. So adaptive meshes, or oftentimes adaptive moving meshes, are really useful when it comes to focusing computational power in regions of a solution domain that might need higher resolution. So it could be that we want to focus computational power around some eddies, but the eddies are localized and maybe not much is going on somewhere else, say in an ocean model. So what you might do is increase resolution around the eddy, but have less resolution in the places where things aren't changing very much, where you don't really need to be tracking the model as much. So this is typically what they've been used for. Oftentimes in some geophysical flows, reaction diffusion equations, these things have been useful for modeling pattern formation. A lot of these models will conserve a lot of these adaptive mesh models will conserve the number of mesh points, but some of them don't. And this is actually a sea ice model called NextSim that comes out of the Nansen Center, Nansen Environmental Center in Bergen, Norway. It's a purely Lagrangian model with an adaptive mesh. What the mesh does, or I should say what the model does, in addition to solving some thermodynamics, the nodes of this model advect with the velocity field of the ice. And I'll show you a movie of that. But what that means is that nodes can get too close together. And when you do that, you need to do some remeshing for your numerical scheme. So here's sort of a schematic of that. You might have two nodes of this triangular mesh get too close together. What you'll do is remove one of them, say the center node, and then retriangulate, right? So you can see this happen in this model, and it looks like sea ice moving here. When it gets darker blue, you're having open water there. But if you look carefully, you can see some of this mesh changing, right, in time as we do the Lagrangian time steps. When this happens, that can create issues, and I'll talk about those for ensemble data assimilation methods. But just to show you one reason you might want to use a solver like that, here's actually the region they were modeling, and hopefully this will play okay. So if you keep what you just saw in the back of your mind, maybe we'll skip ahead here to where it gets interesting. Actually, sorry, we want to look at it open up there. So this is exactly the region that we were looking at. And so you can see that formation of open water happening. So it's able to capture that kind of motion. And that's really important for operational forecasting in the Arctic. Okay, so let me see. So, sorry, I'm stuck. There we go. Okay, so that's just a very short argument for why one would use adaptive meshes. Let me just remind or give a sense for what data assimilation is. In data assimilation, typically you have a model. In this case, I've been focused on sea ice. I've thought a lot about sea ice in my career, but you might have some model and you have some observations. Hopefully you can see my cursor acting as a pointer here. The idea is that you have some DA scheme that combines what you think might be true from your model and what you think might be true from your observation. There are errors in both, neither is perfect. You want to combine them in some way that you get something that is close to what's actually happening. It's a very high level view of it. The better those things are, obviously, the closer you'll get to the truth. So you want to have a good DA scheme. There's a lot of data assimilation methods out there, but the most common ones, you'll hear the term Kalman filter, and a lot of them are related. Some of the basic ingredients in a data assimilation scheme are a model. So in this case, I'm sort of representing a model here as A times X, where XF would be the next time step. So A propagates the model forward, X would be your state variables, for example. But you have some model. You also have some measure of how off your measurements are. So you might assume, and this is often the case, that maybe your satellite measurement is normally distributed with some error covariance matrix R. We call that the observation error covariance. And then that your forecast model is off from the truth, typically with some Gaussian error, and you have a background error covariance matrix. So these are some of the ingredients that typically go into DA. You also have this guy here, H, which is quite important. It's an observation operator. What that does is it takes your model state to the observation. So for example, if I'm assimilating, let's say sea ice concentrations, the way that those are obtained is with a microwave signal using passive microwave radiometry. So really it's just a bunch of numbers, intensities of microwave radiation, which you can turn into sea ice concentration. But you could have an observation operator that might take your ice state model and run the microwaves that should come off of that through the atmosphere and try to obtain those radiances, right? So you're mapping whatever your model state is to whatever your observation space is. Oftentimes it's just a projection if your observations are directly of the variables that you're modeling, but sometimes it's not. Okay, so with these ingredients, there's sort of several approaches that people use. One is often referred to as optimal interpolation. So if you notice here, I have XF, which here we're referring to that as our forecast. That's what our model is saying. I have Y0, which is our observation. That's maybe what the satellite said or the thermometer said. And then I have my observation operator applied to my forecast. So I'm mapping my state variables to that observation space so that I can compare them in the same space. And then I have a scaling thing here, right? If you notice what we're doing is we're saying, here's my forecast, and I'm gonna add to it some scaled version of the difference between my observation and what my model state is saying. And that scaling factor is called the Kalman filter. And typically in optimal interpolation, and actually in this variational method, it has this form. But notice what it involves. It involves the background error covariance, so how confident you are in your model, and your observation error covariance, how confident you are in the observation, and then of course, the observation operator makes its way in there. There's also variational methods where you might optimize over these differences considering the same matrices. It turns out that if your model is linear, the minimizer of this cost function is exactly this guy. They're the same. This is what we call 3D var. There's also 4D var, which is a little bit different, but what that does is you consider all the past measurements as well. So you're looking at how well your model did in the past. And then there's a Bayesian statistics approach. This is just asking, what is the probability of my model state given the observations? And you'd say use Bayes' rule, that's proportional to the probability of the observation given the model state times the probability of the model state. You can play this game in a purely Bayesian way, but if you assume that everything is Gaussian and you do a maximum likelihood, you get, again, this same exact equation for the update. So this is why this idea of a Kalman filter keeps popping up. Under nice linear or Gaussian situations, the Kalman filter is the best way to do DA. Okay, so let me just show you how Kalman filtering might go in a sequential way if you're trying to, say, predict the weather or use an ocean model or something. Typically what you'll have is some state X that you have for your model, and you'll have some background error covariance, how confident you are. What you'll do is forecast that forward in time. So you'll apply whatever model it is to move to the next time step. I didn't really mention this, but you also often update your background error covariances. Then you take that down with your observations. You have your confidence in observations, confidence in forecast. you calculate your Kalman gain, and this is a little bit different form than I showed before. You apply the update to your state. You update your background error covariance, the Kalman gain gets here. So this K1 means at time step 1 or first assimilation step. Then you've got a new optimal state. So XA, I don't think I mentioned, the A stands for analysis. That's what we're saying is our best estimate of the truth. Then we just repeat the process. Forecast, get our observations, apply the Kalman filter, best estimate of the state. And we just sequentially do this as we have observations. That's the general idea. But as you can imagine, it's probably typically hard to know what your background error covariance is. It's hard to know how much confidence you should have in your model. It's also hard to know how much confidence you should have in your observations. And this is where the Ensemble Kalman filter comes in. It's suboptimal in that it's not as good as a Kalman filter if you truly knew all the error covariance matrices, but it gives you a way to estimate them. The basic idea is very similar. There's some true physics. We're off by some amount. But we have a model that we can use to forecast and model our state. We have measurements of that state, however they may be coming in, and they're going to have some error associated with them. But what we do is, in order to estimate that background error covariance, we run an ensemble of the model. And then we use these error matrices here to estimate those the needed background error covariance matrix. So maybe before I talk about these little pieces, let me just show you the picture here. I might initialize my state up here in blue. Then I forecast in time until I have an observation Y here. So Y here might be an observation. So these things will spread apart with all the state variables. Then what I'll do is use those to estimate the matrices I need to calculate the Kalman gain, that K matrix, that scaling factor. I'll estimate it using those ensemble statistics. Then I will apply the Kalman gain with the observation here, and I update each one of those ensemble members individually. So I use the ensemble statistics, estimated ensemble statistics, to calculate an approximation of the Kalman gain, and I apply it to each ensemble member. And then I say that the best estimate of my state is the mean of all those ensemble members. But we update each and every single one. And then you can repeat that process, just forecast, estimate, apply Kalman gain, etc. So this is sort of a picture of that. Here's what we would have forecasted, here's the observation, and then we get some analysis. And so the way that we estimate those is using these error matrices. So if you notice here, I've got F1 through Fn. This is like the first ensemble member through the nth ensemble member. And I'm comparing each of those to the mean of all the ensemble members, right, for the state variables. That's one error matrix that we use. The other error matrix that we use is we apply H, the observation operator, to each ensemble member, and we look at that mean as well. And then we calculate the Kalman gain using these matrices. And this is like the analog of the background error covariance. Here's your analog of your R, your observation covariance matrix. But the upshot is they all go into calculating that approximation of the Kalman gain. And then you just play this game with those Ks, but you're estimating it using these ensemble members. Let me just show you how it works. There's just a fun animation that I can run, and I think is worth just looking at. So let me just run it for you. This is Lorenz 63, if you're familiar with that model. And let's see if this pops up. Hopefully you can all see this. This is the fun one here. So let me see if I can make it any bigger. So here you've got three variables, X, Y, and Z in Lorenz 63. The ensemble members are all these different colors. That's going kind of slow. But the ensemble members are all the different colors. The black line is the truth, right? If you were to do it with a certain initial condition. And eventually we'll see a little observation appear, and you'll see all of the ensemble members get updated. It is going, there's an observation. And then each one is updated based on that observation and those ensemble statistics. And then you just repeat that process sequentially. So it might be, I'm taxing the system with Zoom and PowerPoint and Python all open, but there's actually a link to where you can get this code if you want it at the end of these slides, if it's something that you wanted to play with. But I think it's kind of just fun to look at. And I think this gives a real sense for what's going on. You're seeing the ensemble members spread apart. We're learning about the variable covariances, and then we're able to make updates once we get an observation and continue on. Okay, so I will end that part and go back to the slides. let's see, oh, bunch of figures will pop up here. Okay, so that's the basic idea of the Ensemble Kalman Filter. Okay, so the main point of that is what we do is we estimate the error covariance matrices from that ensemble. That's essentially the key to it. And so if we're going to estimate those, we want to make sure that we're comparing quantities that are A, representative of the same state variable, but also in the same location in space and time, right? So for a standard, say, Eulerian model solved on a regular grid, every grid point of any ensemble member that we might take, like say we have 2 ensemble members here, those grid points are in the same location and we're representing the same variables there. So you might have some state vector full of, if it's ice, I like to think about sea ice, but thickness, well, so temperature, ice thickness, area fraction, velocity in one of these grids, but they're all in the same places. Each one of those ensemble members has the same information in the same spot. I mean, they may be different physical values, but I think that makes sense. So the dimension is the same. But if we're doing an adaptive mesh model, those nodes, if it's a Lagrangian solver or we're moving nodes around, each ensemble member may have those nodes that carry the information in different places. And if it's not conservative, there'll be different numbers of them. So that complicates the estimation of those error statistics, right? We have to know what we're supposed to be comparing. And so you have to come up with ways to deal with that. Essentially, the main problem is that the dimensions of each ensemble member aren't the same. So the general idea is you could say, all right, I have a bunch of ensemble members. They're all on different meshes. I need to find some way to match the dimension, put them on some common space, which I can then estimate the statistics on, and then apply the update. And then maybe I need to move them back to their previous spaces. Maybe that's something we have to do, but just a very general idea. So we started to look at this, and I'll talk about one specific experiment that we did. And everything's harder in 2D or 3D, so you go to 1D first, right? So this will be in 1D. But basically, this is what we assume, and it is motivated by NextSim, the remeshing rules here. But so the idea is we have a PDE. So I've got some PDE here, U of T. In this case, we use periodic boundary conditions. We'll have some initial condition. We have some ordered mesh, which is nice in 1D. And then we have some mesh dynamics. And in this case, what happens is, just like the nodes in say, NextSim, we advect those with the flow. So here, my node location is now a function of time, and its derivative is just equal to the fluid velocity. And the 2 equations that we looked at were Berger's equation and Kiramoto-Shibashinsky equation. This one's a chaotic one. This one has a nice physical shock that the nodes will be tending towards, since the gradients are higher there. Let me just show you roughly how the meshing scheme works. So you've got this moving mesh that's just moving with the flow. It could happen that 2 nodes get too close together, and you might not want that. So what we do is we remesh when that happens. Or it could be that 2 nodes get too far apart and we need to remesh. So we basically just set tolerances. Tolerance delta 1, that's the closest they should get. If they get too close, we remove a point. Tolerance delta 2, if they get too far apart, then we add a new point. And you can see that in this figure up here. It might be a little bit hard if it's small on your screen, but down here in green, you've got your initial mesh, evenly spaced. And let's see, so if we followed, say, these 2 points in time, this is Berger's equation, you can see the shock. They started to get too far apart, and we had to introduce a new point. Or if we are over here and say we follow these 2 points, right, at this point, they got too close and a point needed to be removed, right? So that's the remeshing that's going on. Okay. So we want to do DA with that. And given that each ensemble member will have a different mesh, there can be different numbers of nodes, they'll be in different locations, we need to find some way to compare them. And one idea is to use a reference mesh. So we have ensemble members, we somehow try to do our DA scheme on the reference mesh, and then maybe we do some kind of map. And I'll talk about some work that was done in 2019 by some of the co-authors on the work that we did recently, where they did do this. They actually put each ensemble member on the same grid, did the DA update, and then returned them to their previous grids. But what we'll do is actually update the node locations themselves. Okay, So given that we have these remeshing rules, the way that we can make choices for what that reference mesh needs to be are really sort of naturally two different ways. One could be an equally spaced grid where we have intervals of size delta 2. In that case, since that's the furthest away 2 points can ever be, we're guaranteed that every ensemble member would have a node in one of those intervals. But it could be that, you know, an ensemble member has 2 nodes in that interval. So we'd have to deal with that. We'd have a different number of things. One strategy could be to average these and then do an update, right? But another way that you could do it would be to use delta 1, since that's the, I should say that's the closest 2 points will ever be. So if we do that, then with our grid, we're guaranteed to have at most 1 point in each interval defined by that mesh, that reference grid. So here it might be I have 2 ensemble members, the green and the blue one. Here they both happen to have one in the first interval, but green's missing one here. I think here blue's missing one, you get the idea. These are the 2 kinds of ways that we can make comparisons. And I'll focus on this one. We called this the high resolution, obviously, because it's a higher resolution. And I'll talk mostly about that. This is that previous work that I mentioned, where they were putting things on a fixed reference mesh. This figure is actually kind of hard to understand, but it's a little bit rough. Maybe I should just go to the cartoon, but the basic idea is that on the low resolution mesh, so if we look here, blue might be the ensemble member. And what we do, these 2 points might be in the same interval. What you do is you average them to make 1 point, and you put that on that fixed low resolution mesh, and then you do the ensemble update. And then you return that by, I guess, well, so then when you're done with that, you can go back to your previous mesh by splitting the difference of that. In the high resolution case, really what you just do is shift each node to that reference mesh. And then if you have something on that reference mesh that's empty, you just interpolate to it. You interpolate a point to it. I think I'll show you a cartoon that will make that a little bit clearer. But first, let's just look at what the low resolution, the high resolution meshes do. So if you stare at this figure here, I've got the RMSE errors. The red ones are the analysis. These are just the blue is forecast. Here, HR is the darker color and the pink color is the low resolution. And this is time here. So if you look at the RMSE, this would be the solution compared to or the analysis compared to the truth. You can see they do pretty well. Sometimes low resolution tends to do better than high resolution. For Kiramoto-Shibashinsky, low resolution does worse than high resolution. Might depend on what you want to do, but at least they're doing better than the free runs. So you know that the DA is doing something. If you don't do DA, you get worse results. That's at least what this slide is meant to portray. Okay, so we can take an approach where we simply put all the ensemble members on the same grid and do the update. But here we might want to think that with this AMM model, the mesh structure is actually physically driven by the flow, or oftentimes in many other models, it's driven to satisfy some physical principle, right? Maybe it's conservation of energy, but physics often drives how these meshes change. In sea ice, which is an example that I like, that ice velocity, which might be moving the nodes, well, that's directly tied to the thickness, the drag, and the stress, and the ice concentration, all of these physical things that, at least concentration, certainly you can observe. So you might want to ask, if I have this dynamic mesh, and if it is driven by the physics, can I update that mesh using the physics? Okay, so one question you might ask would be, well, what does that even mean? What is a good mesh update, right? So you could imagine that you start your model with some initial mesh, and you allow that to go with the flow. Let's say you know the true flow. You could lay down markers and then apply your remeshing rules as your nodes were to go through that flow. And then you'd have like a truth grid that you might look at, right? So your true mesh would be the one that you would get tracing through the true flow. Of course, you don't know the true flow. You do know that the flow depends on those physical values. So what I think the best that you can do is just try to update the mesh based on those physical values and let the ensemble statistics and the remeshing rules decide what the best analysis mesh is. Okay, so this is a comparison. This might make it a little clearer what was going on in that previous work. But if we're going to do an ENKF, we have to match the dimension. That's I think the main key here. So before, what we were doing when I was talking about that low resolution, high resolution, this is an example of the high resolution. We might have an ensemble member that looks like this, missing some points in some of those intervals. What we can do, or what they did, they shifted those points to the regular grid, the ones that we had, right? So you see these points getting moved to the grid. And then if there was an empty one, you interpolated a point. So now you have the same number of points in the same locations for each ensemble member. Estimate error statistics and update. And then after you do an update, you shift those points back to their previous mesh and remove ones that were interpolated. But another way that you could approach this would be to leave the points where they were and then just interpolate points where you didn't have any before. That's what's going on here. This one's missing a point, so we interpolate it here. These bars here represent the fact that we're choosing a place in that interval from a normal distribution of the center of that interval. The idea here is that we don't want to bias our statistics to the center of that interval, because in this case, we're going to augment our state vector. We've got our physical velocity values here. Notice the state vector here that we estimate statistics, the location doesn't come into play, but we're adding as a part of the state the node locations. So it's double the size of the state vector, which will go into the calculations of that error matrix. Okay. So this is just another cartoon of how they differ, these two types of methods. We have an ensemble member, we embed them in that common space, however we choose to do that. We'll apply the ENKF and we'll do an update. Here, what I think is sort of important to notice is that when we look at, say, an updated member here, if you notice that the green X's, those would be like the previous locations, the previous node locations. For what we call the HRA case, I should say that's HR mesh, but an augmented state vector, they've moved, right? We've updated the mesh. This is a cartoon. I'll show you some actual results, but this is a cartoon. We've updated that mesh. So those are now in different locations. And to go back to the previous space, all we do is just delete points that were in previously unoccupied intervals. Just go back to the same dimension that we had before. In the HR, your updated member is on that fixed reference mesh, which is fine. It does work. You do get good assimilations. But the way that you go back is you just put those points back to their previous mesh location, right? So what you've done is you've moved things to compare the physical values, you've updated those, and then you just go back to the previous grid, right? And as you can imagine, that shift might cause, I think, a couple problems, and I'll show you what it does. But this is just a flow chart of the two things, and I think the main key here is really this forecast piece here before we apply an update. But the general workflow is you have an initial ensemble, you forward that gives you a forecast, you match the dimension. In the case of just HR, where you put them all in the same grid, these are on the same mesh, so you're not considering the statistics of where the nodes are. But in the augmented state vector, you have different meshes, and those are coming into the estimation of the statistics. So you estimate those, you apply inflation, which is a trick in DA to make it work better. You do your update. You make sure you have a valid mesh in this case. You don't have to here because it's on a regular grid. You get an analysis for each ensemble member that you can use to estimate the state. Then you return the dimension. And then I've got a box here that's in both apply jitter. I'll talk about what that is and why it's necessary, but it's another form of inflation. And then you repeat that process. So you just follow this circle all the way through. Okay, I probably have too many slides on this, so I'll skip this one, but this is just a cartoon of what it might look like. Here you have some observations that you're updating your ensemble member with. But this is something that, yeah, so this is what it looks like, say, for Berger's equations between the two methods. On the top, you have the HR going through, and on the bottom, you have HRA. The filled in black circles are the analysis means. That's the average of the updated ensemble members. The green pluses are the forecast members before the update, and then the blue circles are the analysis ensemble members. Remember, we update each one individually. So this is just looping through. But there's something that's, I think, nice to notice here once it sort of starts over. Although at the end, you notice that the augmented's losing track. But if you look at this on the bottom, you can see how all the ensemble members are lining up along that curve. And that's because we're updating those node locations. On the top, they're all in the same place and you have sort of a spread in Y, right? And that's actually a result of the shifting. You're doing an update and you're saying this is the best estimate for the points on this regular grid, and then you move those to a new place. It's a small movement, but it does disrupt the curve a little bit. It actually turns out to be beneficial though. So if we look at the difference in the RMSEs for these, the red, maybe focus on the red ones, those are the analysis. The HR, where everything's done on the same grid, is in dark red, and HRA with the augmented state vector, where we update the nodes, is in pink. And you notice the HRA does a lot better at the beginning, but then something happens and we start to lose track. We're not updating the solution anymore, whereas this one is managing to do that. And that's where we would apply inflation. What's happening is that the ensemble collapsed to the solution so quickly that we had very little variance in where the members were. And that means that we'll ignore the observations. The Kalman gain will say, don't do any updates if we have no variance in that solution. So one way you fix that, oh, and I should say, let me just show you why we might want to add some inflation. So this is an example of what all the ensemble members might look like for each of the methods. On the left is HR, where we're on a fixed grid. And on the right is HRA, where we're updating the node locations. So here, if you look at this red curve, that's just one ensemble member. And you can see little wiggles in that line. That's because we're doing an update and then moving the points, right? That's disrupting things. But what you see also is blue here, that's just at that regular grid, that's just all the ensemble member points plotted at that spot. So you see the spread that you're getting from there. And these are at the same time here, whereas you see almost no variance. All of the blue little ensemble members are just all collapsing around that solution, right? So you don't have a lot of variance, and that causes problems in the ENKF. So one way to try to fix that is to add some noise to your model. So here, for the HRA method, what we do is we forecast, we interpolate our empty intervals, we do our updates. So here you're saying these are observations. We update the ensemble member based on the observations that we get, which we get from a truth run, I should say. But then after we do the update, we add noise. That's these little bars here. We add noise to each point, just random white noise with some mean. When we do that, and it's done in a way that looks at the amplitude of the velocities. But when we do that, this is what the runs look like. So at the beginning, we're not adding much noise to this at all. So at the beginning, things look the same. But if you focus down here, where's my mouse? Down here at the bottom, you'll notice that we start to get that noise added in. And now, rather than forgetting the solution, because we've increased the variance in our ensemble, we're able to actually track that solution quite well, right? If you notice the black filled in circles, that's our best estimate of the state. And it's pretty much lying right on the line. So then if we look at the RMSE errors there, we still do better at the beginning, but then we're able to actually do better at the end. The light pink being below the red is what we want, right? So we have to add some inflation. So the same thing happens in Kiramoto-Shevashinsky. If you notice down here, these ensemble members are all just lined up along the curve, and that's great. Here you see all that noise induced by the shifting back and forth, right? Here's the RMSEs. Turns out that the shifting back and forth is still helpful. HR, the dark red, is doing better than HRA, the augmented state vector. But if we play the same game and add in some noise, we can fix that problem. So now if you look at the bottom, you see that spread being increased in those ensemble members as we go through. And then you're able to do a little bit better than you otherwise would. So that's the argument for inflation. So I should say that there's actually two types of inflation going on here. And for those that aren't familiar with Ensemble Kalman filters, you often do multiplicative inflation, where you just multiply your error covariance matrix by a number between 1 and 2. Typically it's like 1.1, 1.3, but you just you artificially increase those covariances. And then there's additive inflation, which is what I was calling that jitter, where we add some noise to the ensemble members. So one question you might ask is, if I'm gonna be using these, which is standard in the ENKF world, which values give me the best results. So one thing we did was for both methods to try to study how those things, which parameters will give us the lowest RMSE errors. So on the left column here, you have an example of that. This is just a contour plot of the RMSE, time averaged RMSE error. The top is HR, the bottom is HRA. And the red star represents that lowest value. What's interesting here, so this is the amount of additive inflation on the y-axis, multiplicative inflation on the x-axis. If you notice though, for HRA, it's beneficial for both, right? Even for HR, we do better when we do some of that additive noise. But for HRA, you can really see that without it, you have a problem, right? When the ensemble spread collapses so quickly, because you get good updates to start. And the same is true for Kiramoto-Shibashinsky. Down here, you can see that, I don't know if it's hard to see on your screen, but the darkest blue is not along the zero jitter additive inflation axis, right? We need some to get a good assimilation. Okay, so if we do that, if we go through for each of the methods and pick the optimal inflations, and then also look at how things change with the ensemble size, the initial mesh size that we use, and the observation error that we use, we can see how the schemes stack up across a variety of different situations. So this plot here, on the top, we've got for Berger's equation, the time averaged RMSEs, and for Kiramoto-Shibashinsky. For each of these settings, 20, 30, 50 ensemble members, we're using the optimal jitter and inflation for each method, right? The one that we get running through that space and then picking the minimum. So for Berger's, you see blue here is HRA. You typically do better in RMSE, or at least about the same sometimes, but often better. For Kiramoto-Shibashinsky, you do better, and as long as the observations are good enough, you do better, right? So that's good. That's a good result. You're doing a better job of assimilating. This is just what those estimated error covariance matrices look like. This, I think it's interesting. And what I want to point out here, so I should say, notice up here, I've got that error covariance matrix. So sigma is standing for the covariance. In the top block of that thing that we would use to estimate our Kalman gain, we'd have the covariances between the velocity values, the physical values. In this bottom diagonal block, we'd have the covariances of the node locations compared to the other node locations. And then in these off diagonals, we'd have the physical variables compared to the node locations, the covariances between all of those. I'm not showing those, but in red here, these are the physical values, and then these are the node location values. And I think what's really cool with Berger's, I mean, you see the shock right there. This is at a particular time, but there's the shock in Berger's equation. For Kiramoto-Shibashinsky, these are the height, the strong gradients, the rapid ups and downs of that wavy profile. But with HR, where you put everything on a fixed grid, you get these spurious long-range correlations that aren't really real. And that's because you've shifted things, right? And so it may be better for the sake of having good statistics to really just augment your state vector and leave things where they are and then compare those. Another reason for that is what happens when you look at the covariances between the physical values and the node locations themselves. So that's what I'm showing here. This left one is Berger's equation. And I should say for HRA, right, let me just state for HR, you don't have, you only have this red upper block, right? It's a different matrix, but you get this much larger matrix when you include the node locations. But this is, I think, really cool and really striking. When you look at these covariance matrices, first there's the shock, right? So here you've got physical variables and compared to your node locations. But if you plot the diagonal of that, and then you look at the spatial gradient of your solution, you're mimicking that spatial gradient with your covariances. So blue is the derivative of the velocity field with respect to x. And then you look at that covariance, it's taking on the shape of that gradient. What that means is you're bringing in that derivative information into your estimations of ensemble statistics. And it's playing into how and how much you do an update. And I think that's really cool, given that the nodes are actually physically driven, right? Okay, but before what we had to do was do all this additive inflation, right? We were adding all of these things. And I just talked about how neat it is to think about derivatives. If we're gonna add so much random noise to a method like this, we might actually be concerned about what that does to the ensemble members. So I call this PDE fidelity. If I initialize my PDE and I run it, the solution will typically have a specific kind of shape based on whatever that initial condition is. But if at these intermediate time steps, when I do assimilations, I add random noise to that, I'm violating that, right? I'm screwing up the solution in a way. And this is actually kind of interesting because you can have, if you notice over here, so this is Burgers again. If you notice over here on the right, black is the truth. Your analysis mean, which we say is the best estimate of our state, is this red dotted line. This looks really good right here, up here and down here, right? It's sort of lying right on the truth. But this is just one of the ensemble members. I mean, that's a mess, right? That's just a wiggly line. But when I average those, I get something close to the truth, right? And if that's all you care about, then that's fine. You keep doing this, you've got low RMSE. But there might be a situation where you want the ensemble members to retain that sort of proper shape and have the right derivatives, say, right spatial derivatives. Maybe it's because it's an incompressible fluid. I don't want the divergence of U to stop being 0, right? I want to preserve those kinds of conservation laws if they're important. So you may want to make trade-offs in RMSE to protect your ensemble members. So if you notice here in the middle, I'm actually showing what the best RMSE you could get at this time was. So they're the same there. Those are the settings, 1.13 additive inflation, or multiplicative 0.2 additive. But if you come over here where things look a lot better, you're not necessarily that different from the RMSE, right? So you might want to have some other metrics that help you diagnose what's going on. One thing that we did actually look at was the RMSE of the derivatives. So now this is the same as before, but notice we're looking at the spatial derivatives of each of the methods. And this is set for the optimal parameters, not for the derivatives, but for the functional values of the RMSE. But then we just look at the RMSE of the derivative. And so for Burgers, HRA does better, and you'd kind of expect it to do better, again, because we're bringing in that derivative information into the covariance matrix. And you do typically do better. For Burgers, there are places where it doesn't, especially if the observation error gets too large. But for Kiramoto-Shibashinsky, you're getting massive improvements, I think, by considering those node locations. There are other things you can look at too. One thing that we took a look at, because again, it's all about the metrics that you choose. We looked at the difference between the ith ensemble member and the truth at an assimilation, at a specific assimilation, well, at all the assimilation times, I should say. So you might define, though, that difference at assimilation time tau j, just ui minus ut. What is the physical value? What is the difference between your ensemble member and that at the truth? And then we looked at the ensemble average of the time average of the variance of that difference. What that would measure is if you're doing well, good assimilations, your average on that should be about 0. It should be like mean 0. So if you think of your variance for that, that's telling you how often you're deviating from that mean. That's telling you maybe a little bit about how wiggly your curve is, if your difference is normally 0. So you can look at that. You can look at the kurtosis of that difference as well. What the kurtosis tells you is how normally distributed something is, or how rare something is. So in this case, a kurtosis of 3, the way that we calculated it, would mean normally distributed with some variance sigma. A kurtosis larger than 3 would mean that everything is tightly, your distribution is tight around the mean, meaning that deviations from the mean are very, very rare. If it's a very low kurtosis, it would say that large deviations from the mean are very common. It's a very flat distribution, heavy tails, right? So the idea here is that, and then of course RMSE is kind of standard, but here you're looking at the average RMSE of the ensemble members, not the analysis members. But the idea here is that you want a low sigma ends, you want a low RMSE, average RMSE amongst the ensemble members, but you want a high kurtosis. And the idea is that if your deviations from that mean are very rare, and that large deviations from that mean are very rare, you're looking more like this up here rather than wiggly here, right? So if you notice, here are some of the values. For this one, you've got a very small variance, a large kurtosis, nice curved line on the truth, nice shape to it, right? It's not wiggly, and then a nice low RMSE. Here you've got higher values for sigma and RMSE, but a very low kurtosis. And you're seeing that because these large departures from a mean, being close to the solution are quite common here. right? If that makes sense. Okay, so that's just something else you can look at, and then you can play games, I think. And I think it's something that people don't often do, but if you care about that PDE ensemble member fidelity, if it's important for what you're modeling, you may want to run experiments with your inflation parameters to see what these other metrics might be doing. And I'll just point out that this is for burgers here. If you notice, you have the highest kurtoses when you have the lowest additive inflation. That makes sense, right? You're not adding a whole bunch of noise to things, right? But you can gauge how well that's going for all of these metrics. Okay, let's see. So this is the last slide. Just essentially, adaptive meshes are sort of an up and coming thing. People are using them because it helps you leverage computational power to focus on regions that you need to model closely. But they get in the way of ensemble data assimilation methods, but you can overcome them. But you want to think about how you're overcoming them, right? We saw that you can really mess up your derivatives if you shift things around or you add too much inflation. And that's important because we have to do tricks to overcome those issues. If your adaptive mesh is physically driven, I think it's important to note that your node locations carry information about the system. You want to understand what your DA scheme does to those ensemble solutions. And I should say ensemble methods are quite popular in numerical weather prediction, geophysical modeling. People use them quite often. I think it's important to think about other metrics other than RMSE. And you might want to develop new metrics that you can use in new DA strategies and incorporate into the existing methodology. And then I'll just say that this work that I presented, we actually just submitted our revisions last week, but there's a version of it on arxiv. There's the link. But if you want to play with some of that DA code that I showed that animation with, you can go to this website from GitHub, the Nansen Center. They've got these DA tutorials in Python where if you go through them, you learn a lot about building an Ensemble Kalman filter, and you can play with those. And you can work through them on like this Google Colab platform. So you don't actually have to install Python on your machine. You can sort of run it in the cloud if you want. It's kind of fun to work through. I'd recommend it if you're interested in data assimilation. And with that, I'll just say thank you.
Thank you very much.
All right, thank you for the great talk, Chris.
Yeah.
If there are any questions, feel free to unmute yourself and ask the question yourself to Christian, or to type them in the chat, and I will forward them to him. In the meantime, could you please share us the archive and GitHub link in the chat so that I could copy paste them?
Yeah, for sure.
Thanks. Unfortunately, we cannot click anything on share screen.
Yeah, that's true. Let's see here. Let me be able to grab that. Let's see, maybe I'll have to stop sharing to get to the chat for a second. So there's the archive link, and yeah, these DA tutorials are actually great. Emmanuel's seen them before. We did a summer school this summer that he was a part of. I think, did you come to that where we went through some of these? I don't know, you might have been in a different.
Yes, I went through it, yeah.
Okay, so you've seen those before, yeah.
Thanks for